In the last session of a lab work of a design of a two-stage gearbox, we have seen introduction to gearbox. This is session 2 regarding design of a two-stage gearbox. In this, we will see design procedure for spur gear, then how to decide gear ratio in each stage when total gear ratio is known to us. But before starting design of a spur gear, we'll see significance of the gearbox and main components in a gearbox. So significance of the gearbox, mainly gearbox is required because in an automobile, high torque is necessary when climbing hills and when starting, even though they are operating at low speeds. Then, if vehicle is running at high speed on level roads, then high torque is not required because of constant momentum. So, here there is a necessity of a device which will change the vehicle torque and its speed according to road condition. So according to road condition and according to requirement, we can change the torque by using gearbox. Then components of gearbox. First, shaft is required. As power transmission is taking place, power transmission will take place with the help of shaft and gears. So shafts for mounting gears, then keys, bearings to support shaft and gears. Whole assembly will be, it should be protected, and for that purpose, gearbox housing is there. It will also hold lubricant and it will protect gear assembly from dirt and dust. Then provision to prevent axial movement of the shaft relative to bearings and to prevent axial movement of the bearing. Then space for oil reservoir because lubrication used is a oil. Then if oil level is adequate or it is too low, so we will fill the oil. So oil level indicator is there. Then drain plug and inspection hole. Why drain plug? Because after continuous using, after some cycles, viscosity of oil will get reduced and it will be no more provide effective lubrication. So that oil should be removed and it should get replaced by new oil. And for that purpose, drain plug is there. Then in as gearbox may operate at high speeds, so there is a friction and there can be heat generation. So cooling purpose, to expedite the heat dissipation, cooling fins are also provided. Then provision for easy assembly and disassembly. So these all are components of gearbox. Next we'll see stages of the gearbox. In a single stage gearbox, speed get reduced in a one stage from high speed to low speed. So here schematic arrangement is shown. You can see this is the shaft 1 and this is shaft 2, shaft 1, shaft 2. Gear 1 is mounted on the shaft of, it is a high speed shaft, and gear 2 is mounted on the second shaft. Now speed, here input is what? High speed. So gear 1 will rotate at high speed and it is meshing with gear 2, and speed will get reduced and it will be output over here at second shaft, that is a low speed. So speed reduction takes place within a single stage using one pair of gear. One pair means two gears. So it is known as a single stage gearbox. Then two stage gearbox. In a two stage gearbox, here there are four gears and speed reduction takes place within two stages. So it is known as two stage gearbox. Now you can see over here, high speed shaft, or here input is over here, and it is intermediate shaft. You can see this is a input shaft, this is intermediate shaft, and this is output shaft where speed reduction is required. Here you can see this arrangement is bevel gear arrangement is here for a first stage, and for a second stage this arrangement can be spur gear or it can be helical gear. Okay, so this is a pinion bevel gear, high speed shaft is there. Pinion bevel gear is mounted on the high speed shaft. It is meshing with bevel gear, and bevel gear is mounted on the intermediate shaft, and pinion of the second stage gear, this is a pinion of the second stage gear, is mounted on the same shaft. So according to law, or if you have studied a gear train, bevel gear, whatever speed with that bevel gear will rotate, with that same speed pinion of this second stage will rotate, and it will mesh with gear of the second stage. Now gear of the second stage is mounted on this output shaft and will get required speed reduction over here. And this yellow part you can see over here, it is a casing. Okay, and here it is attached to required application. So it is a two stage gearbox. Now in our study there is a two stage gearbox, design of a two stage gearbox. So first, what are the objectives of this? First you have to decide type of gearbox and selection of a gears for given application, and then design of a gear pair according to that. So first we will see one problem statement for design a two stage gearbox. Problem statement is here: a 15 kilowatt electric motor running at 1440 rpm drives an agitator running at approximately 150 rpm. Assuming the motor shaft and the agitator shaft parallel, and assuming suitable data wherever necessary, design a two-stage gearbox completely. So, what are the given things over here? First, you have to find out what are the specifications given to you, and according to that, you have to design the gearbox, right? Power is given, which is 15 kilowatt. Input speed is 1440 rpm. Output speed is 150 rpm. And what is the application? That is the agitator is the application for which we will design a gearbox. Then what is assumption you have to make? That motor shaft and agitator shaft parallel to each other. Correct? Parallel means only possible arrangement over here is either spur gear or either helical gear. Remember that, because when two shafts are parallel to each other, we can use only two types of gears, that is spur gear and helical gear. So here specifications identified: input speed 1440 rpm, output speed 150 rpm, shaft position parallel, then input power 15 kilowatt, then input device electric motor, and output device is agitator. Correct? So output device is agitator. Then first step while designing is is select the gears and type of gearbox for given application. Now, how will you decide that? That is the main question over here. So, generally, you find out total speed ratio. Here, some thumb rules are there. If total gear, so according to gear ratio, stages of gearbox will decide it. If total gear ratio is less than 6, then it is single stage gearbox. If stages of gearbox greater than 6 but less than 36, if gear ratio is total gear ratio is less greater than 6 but less than 36, then two-stage gearbox is required. If total gear ratio is, is greater than 36 but less than 216, then three-stage gearbox is required. Now, generally recommended speed reduction for spur and helical gear is 6:1. So this is the general speed reduction. Then now here Total speed, out input speed is 1440 rpm and output speed is 150 rpm. So gear ratio will be 1440 divided by 150. You will get 9.6. So obviously it is ranging in between 6 less than 9.6 less than 36. So two-stage gearbox is required for this particular application. Then first it is a step 2. Once decided that is it is a two-stage gearbox, then we have to design the gear pair. So for designing the gear pair, first 2.1, determination of a speed ratio and gearbox stages. Speed ratio of a speed of a pinion to speed of gear. So total speed ratio GT. Why we are calling as a GT? As it is a two-stage gearbox, so gear ratio for a first stage and gear ratio for a second stage, that will be different. And for that purpose, empirical formulas are available. And speed ratio, that is input speed divided by output speed, is known as a total speed ratio. So we are denoting this letter GT. So speed ratio GT is equal to NP by NG is equal to 9.6, where NP is speed of pinion and NG is speed of gear. Now, to decide gear ratio in each stage, here G is equal to nth root of GT is equal to 3.098, where GT is what? Total gear ratio and N means number of stages, where N means N number of stages of gearbox. Okay. So here number of stages equal to 2 and total in this case only it can be 3-stage gearbox if gear total gear ratio is greater than 36, correct? So so if number of stages equal to 3, then it is cubic root of GT. Here it is square root of total gear ratio. GT is 9.6. You will get here G1 equal to G2 is equal to 3.098. Right? But we are not going to use this formula. So we are going to use another empirical formula which give better design. And that formula is G1 is equal to zero point 0.8 in bracket GT square into K1 by K2 raised to 1 by 3. So G2, so you will get over here G1, right? You will get over here G1 And then after getting G1, you can find out G2, that G2 is equal to Gt by G1. So according to that, you will put the values over here, that G1 is equal to 0.8, Gt is 9.6 square into K1 by K2 raised to 1 by 3, where K1 is, that is load factor, and that depend upon hardness. If you remember that K1 is equal to 0.16 BHN by 100 square, so that depend on the material properties. Here we will assume that both the gears are made of same material, so K1 and K2 will get cancelled, and only remaining thing will be over here is if K1 is equal to K2, it will get cancelled. So if K1 equal to K2, so only thing will remain is what? 0.8 Gt square raised to 1 by 3. So you will get G1 over here, and then after putting the value of G1, and already you know total speed reduction ratio. So G2 is equal to Gt divided by G1, right? Next, selection of number of teeth on pinion and gear. So already speed ratio is known to us. Then to avoid interference, minimum number of teeth for 20-degree pressure angle system, because here what we are assuming, gear gears are having full depth involute tooth profile. Gears are having full depth involute tooth profile. So to avoid interference, minimum number of teeth on pinion should be 18. So number of teeth we have decided. We know the speed reduction ratio for that particular stage. Then next step 2.3, selection of a material for gear pair using design data book. So selected material for that particular speed ratio, and it is for pinion it is C45, and for gear it is C35 MN75. Once material is decided, you will come to know the properties of that material, because what is required over here, that is SUT, correct? Then after selection of the material, next is determination of beam strength and wear strength. So beam strength is given by beam strength is given by SB is equal to sigma B BMY, where sigma B is permissible bending stress of gear material. Now, how will you decide sigma B? We know that sigma B is equal to one third of SUT. Sigma B is equal to one third of SUT. And B is face width of the gear tooth, which will be 10 times the module. M, module of the gear. Y, Levy's form factor for the gear, and Y is equal to 0.484 minus 2.87 divided by Z. For a pinion, it will be point YP. We'll denote that by letter YP, and YP will be equal to 0.484 minus 2.87 divided by ZP. And for gear, it will be YG, and that will be equal to 0.484 minus 2.87 divided by ZG. So YP is what? Already we have studied, correct? This. It is just I am repeating this procedure. So YP is what? Levy's form factor for a pinion. YG, Levy's form factor for a gear. ZP, number of teeth on pinion. ZG, number of teeth on gear. Next, determination of dynamic load acting on gear tooth using velocity factor approach. Why velocity factor approach? Because right now we don't know the module. Design of any gear means what? You have to design means you have to decide the dimensions, and dimensions of the gear depends on module. So design of the gear means first you have to find out the module. So we'll design the module considering velocity factor first. That is the first approach. And velocity factor here kV for a spur gear is equal to 6 divided by 6 plus V. And then selection of factor of safety. After that, after selection of factor of safety, how will you select that determination of effective load? After that, F effective is equal to factor of safety into beam strength, and F effective is equal to factor of safety into wear strength. Now what is wear strength? Wear strength we know Fw is equal to dpbqk. Wear strength is equal to dpbqk. Now design will be based on critical criteria. Design will be based on critical criteria, correct? So whichever is having less value, that will be our design criteria. Next, here power is given to you, speed is given to you. Power is known to us as well as Just wait. So F effective. So preliminary design of a gear pair is using velocity factor. Already we have decided that velocity factor is 6 divided by, so it is 6 divided by 6 plus V. Then we can, F effective is equal to K km Ft by Kv, where K is a application factor. Here application is what? Agitator. And Km is what? Load distribution factor. So you have to select this from tables, that is K and Km. Velocity factor is 6 divided by 6 plus V, and Ft is a tangential load that we can find out from given power, where power is 2 pi nt by 60, right? And torque is Ft into R. Now, how will you decide that application factor? That we'll see. Now, while decide first K, now service factor or application factor is